Hello everybody, welcome into another lesson. So today we are going to do some very basic trigonometric identities. We are going to talk about what are called Pythagorean identities and then periodic identities. So far when we've talked about trig identities, we've already had the reciprocal identities for trig functions, such as for example, your cosecant being 1 over sine, your secant being 1 over cosine, your cotangent is 1 over tangent or cosine over sine, and then your tangent is sine over cosine or 1 over cotangent. We've also talked about even and odd trig identities where your cosine and your secant functions are even, and then your other four trig functions are odd. Well, today we're going to talk about Pythagorean and periodic identities. And the Pythagorean identities get used all the time in calculus. So these are very important. So the first one we have here is the cosine squared of theta plus sine squared of theta equals 1. This is true no matter what angle you pick in existence, as long as they're the same angle. So the idea is here you have some x and y on the unit circle. You have x squared plus y squared equals your radius squared. And the radius on a unit circle is usually 1. It's based off of radius 1. Now this x squared plus y squared equals r squared will actually tie into the very next lesson when we evaluate trigonometric functions of any angle. But, so you have x squared plus y squared equals r squared. Your radius is 1. Well, 1 squared is just 1. Well, we've talked about where x equals the cosine of the angle, right? So you could substitute cosine in for x, which would give you cosine squared of theta. And when you do trigonometric functions, a cosine of theta, that quantity squared is written cosine squared of theta. And that's how it is for all trig functions. If you have a trig function to any power, that's just how it's written. And then your y equals the sine of the angle. So you could substitute the sine of theta in for y, thus giving you that cosine squared of theta plus sine squared of theta equals 1. That is a very fundamental trig identity. There will be times you'll have to manipulate this. You'll also end up getting that the sine squared of theta equals 1 minus the cosine squared of theta. That's if you wanted to get sine by itself. You can turn this into an identity with cosine. Or if you wanted to get cosine by itself, you could say that the cosine squared of theta equals 1 minus the sine squared of theta. Those are all based off this Pythagorean identity of cosine squared of theta plus sine squared of theta equals 1. And again, these occur all the time in calculus. So these are very, very important. There are three fundamental trig identities we're going to learn and we're going to use in the future. So we've covered the first one, where you have the cosine squared of theta plus the sine squared of theta equals 1. And it doesn't matter what angle you pick as long as they're the same angle. That's why we're not specifying an angle. So that's your first one. Next up, we have another one where you have 1 plus tangent squared of theta equals the secant squared of theta. So we have 1 plus the tangent squared of theta equals the secant squared of theta. Well, let's prove that real quick. So you can take 1 plus the tangent squared of theta. Well, okay, on the left side you'll still have 1 plus, now what is the tangent of theta? That's the sine of theta over the cosine of theta, so this would actually be sine squared of theta over the cosine squared of theta. Okay, now the goal of course would be to get a common denominator, right? So if we did that, you would end up getting cosine squared of theta plus sine squared of theta all over the cosine squared of theta. Well, hang on a second. What's cosine squared of theta plus sine squared of theta? That's just 1, right? So this would turn into 1 over the cosine squared of theta. Now, what's 1 over the cosine squared of theta? That's secant squared of theta. So therefore, that proves this identity that 1 plus tangent squared of theta equals secant squared of theta. So let me write this above it, and we're going to do one more Pythagorean identity. And again, I cannot emphasize this enough. These are used all the time in calculus. All the time. Especially in Calc 2. Maybe a little bit in Calc 1, but Calc 2, they really hit it heavy with the trig. And of course, off of this 1 plus tangent squared of theta, you can also say that the tangent squared of theta, if you wanted to get that by itself, is equal to the secant squared of theta minus 1. That's another way you can twist the tangent function around into a secant. And this is especially useful if we were being asked, we're not going to do this today, but let's say you had a problem like the integral of the tangent squared of theta d theta in calculus. This is a calculus problem. You could actually find a problem like this in Calc 1. It would be particularly useful to know that you can make the tangent squared of theta into the secant squared of theta. I'll just do this real quick. So this would turn into the integral of the secant squared of theta minus 1 d theta, which would end up giving you the tangent of theta minus theta plus some constant, which we call c. But that's a calculus problem for another time, but that's where it's useful to know. Okay, then we have one more. There's also, you have 1 plus the cotangent squared of theta equals the cosecant squared of theta. That's also that's another useful Pythagorean identity, and these are really the only three. 1 plus the cotangent squared of theta equals the cosecant squared of theta. Alright, so let's prove this one real quick. So 1 plus the cotangent squared of theta, what's that equal to? Well, that would be 1 plus, now what's the cotangent of theta? That's cosine over sine. So this would be 1 plus the cosine squared of theta over the sine squared of theta. And the goal again is to get the same common denominator, so this would turn into sine squared of theta plus cosine squared of theta all over the sine squared of theta. Well, what's sine squared plus cosine squared? That's just 1, right? So you would end up getting 1 over the sine squared of theta. Well, what's 1 over sine squared? That's the cosecant squared. So that would equal the cosecant squared of theta. Therefore, this identity holds of 1 plus cotangent squared of theta equals the cosecant squared of theta. So these identities, again, I cannot emphasize this enough, folks. These come up all the time from here on out. So if you remember nothing else, please remember these. Alright. So those are your Pythagorean identities. Now, we also have what are called periodic identities. And what do we mean by periodic identities? So yes, trig functions are periodic. That means they oscillate on and on infinitely. And in a couple lessons from now, when we get into graphing trig functions, you're going to see what I mean by they're being periodic and oscillating. But it's important to know that if you take the sine of 90 degrees minus theta, that's equal to the cosine of theta. And then if you take the cosine of 90 degrees minus theta, that equals the sine of theta. So a function of 90 minus an angle equals the cofunction of that angle, because sine and cosine are cofunctions of each other. Thus the sine and the cosine. You can apply the rules to the secant and cosecant also. The cosecant of 90 degrees minus theta would just equal the secant of theta. And then if you took the secant of 90 degrees minus theta, you would get the cosecant of theta. And then you can even do it with the tangents. So the tangent of 90 degrees minus theta is equal to the cotangent of theta. And then likewise, the cotangent of 90 degrees minus theta is equal to the tangent of theta. So if you take a trig function of the quantity of 90 minus an angle, it's the cofunction of that angle. So these are your periodic identities. I'm going to prove it to you with a 30, 60, 90 right triangle. So let's set up our 30, 60, 90 right triangle. So 30, and again, it doesn't matter what angle, but it's probably easiest to demonstrate with a 30, 60, 90 right triangle. Okay, so let's say I want to do, if I take the sine of 90 degrees minus 30 degrees, that's saying that should equal the cosine of 30. So this is the same as saying that the sine of 60 degrees would equal the cosine of 30 degrees. Well, is that true? Let's prove it. So what is the sine of 60? Opposite over hypotenuse, that gives you the square root of 3 over 2. Now what's the cosine of 30? That's the adjacent over the hypotenuse. Well, that's also the square root of 3 over 2. They certainly do equal each other. So this is just one of infinitely many examples you can use to prove that the sine of 90 minus the angle equals the cosine of that angle. Heck, let's do, alright, so the tangent of 90 degrees minus 60 degrees, so 90 minus 60, 60 is our theta, that's saying that equals the cotangent of 60 degrees. So this would mean that the tangent of 30 degrees is equal to the cotangent of 60 degrees. Well, again, does this hold up? So tangent of 30, opposite over adjacent, that'd be 1 over the square root of 3, which is the square root of 3 over 3. Well, what's the cotangent of 60? That's adjacent over opposite. That'd be 1 over the square root of 3, which is also the square root of 3 over 3. So this here proves that the periodic identities also work. All right. So those are all your periodic identities. Now we're going to do a few problems here. So you've got a triangle here where you're given that the cosecant of theta equals 3. You're given that the secant of theta, well, it's not a triangle, they're just two quantities. degrees. The secant of theta equals 3 times the square root of 2 over 4. So they give you two values here. They give you the cosecant of theta equals 3. The secant of theta equals 3 times the square root of 2 over 4. They first want to know what's the sine of theta. So what is the sine of theta? Well, that's just the reciprocal of the cosecant, so that would be 1/3. Sine of theta is 1/3. That's easy enough, right? What about the cosine of theta? Well, that's the reciprocal of the secant, so that would end up being 4 over 3 times the square root of 2, which you got to rationalize the denominator. So this is going to turn into 4 times the square root of 2 all over 3 times 2, which is 6, which would be 2 times the square root of 2 over 3. That would end up being the cosine of theta. We got a couple more they want to ask you. What about the tangent of theta? This gets fun. Alright, so the tangent of theta is equal to your sine over cosine. So let's even write that. We got our sine and cosine already. Well, the sine in this case was 1/3, so this would be equal to 1/3 divided by 2 times the square root of 2 all over 3. Well, this turns into a complex fraction, so you would end up getting 1/3 times 3 all over 2 times the square root of 2, which would end up giving you 1 over 2 times the square root of 2. So you rationalize your denominator, which would give you a tangent value of the square root of 2 over 4. So you got your tangent. Now here's what they're going to ask you. They're asking you for the secant of 90 degrees minus theta. This is a periodic identity. What's true about the secant of 90 minus theta? That equals the cosecant of theta. Well, we already have a value for the cosecant. That's just going to be 3. So the answer to that would be 3. I got a few more examples here. All right. You're given that the secant of theta in this case equals 5. And then you're also given that the tangent of theta equals 2 times the square root of 6. Okay. So what they're asking you now is what's the cosine of theta? Well, that one should be fairly easy. The cosine of theta, that's just the reciprocal of the secant, right? Reciprocal of 5 is 1/5. So that one's fairly easy. Cosine's 1/5. What's the cotangent of theta? We don't even have to get too complicated with it because the cotangent's just the reciprocal of the tangent. So this would be 1 divided by 2 times the square root of 6, but we have to rationalize the denominator. So what you should end up getting is the square root of 6 all over 12. That would be the cotangent of theta is going to be the square root of 6 over 12. All right. What's the cotangent of 90 degrees minus theta? The cotangent of 90 minus theta, again, this is a periodic identity. This is just going to simply be the tangent of theta, which we already have a value for. That's 2 times the square root of 6. Then they want to ask you one more question. here's a good one. What's the sine of theta? So, what is the sine of theta in this case? Well, we know for sure that's the missing fact. Now, we know that the tangent of theta equals the sine of theta over the cosine of theta, right? Okay, we can solve for the sine of theta because we have the tangent and we have the cosine. So this is really going to be equal to, well, let's do this here. Tangent was 2 times the square root of 6. That's going to equal your sine of theta all over 1/5. Now you just multiply both sides by 1/5. You would end up getting that the sine of theta would equal 2 times the square root of 6 over 5 if you multiply both sides by 1/5. So your sine of theta would equal 2 times the square root of 6 over 5. So yes, sometimes you have a little bit of algebra mixed in with your trig. Now the next couple, it seems to be that they only give you one trig function and you got to find a few without even having to draw a triangle. So you may also see sometimes an angle alpha. Sometimes they'll call it alpha as opposed to, that's the best way I could draw my alpha, as opposed to theta, or they could use really any Greek letter or any variable to represent an angle. So you're given that the cosine of alpha equals 1/4. First they're asking you what is the secant of alpha. Well, the secant's just the reciprocal of cosine. The reciprocal of 1/4 is just going to be 4. So that one, that's fairly easy. Alright. Next they're going to ask you for the sine of alpha. Well, you may want to draw a triangle for this. You probably do want to draw a triangle for this. If we have an angle alpha, here's alpha. I'm trying to make it look too much like an A. Here's your angle alpha. So the cosine is 1/4. Let's figure out the missing side. So 16 minus 1 is 15. This would be the square root of 15. Okay. So what's the sine of alpha? Opposite over hypotenuse, that's going to be the square root of 15 over 4. Sometimes you have to draw a triangle when you don't have a choice, but that's okay. Next, they want the cotangent of alpha. So the cotangent of alpha, it's easy since you have your triangle. That's adjacent over hypotenuse, which would be 1 over the square, adjacent over opposite. That'd be 1 over the square root of 15, which would give you the square root of 15 over 15. So there's your cotangent, and then they're going to ask you for what is the sine of 90 degrees minus alpha. That's another periodic identity. The sine of 90 minus alpha is the exact same thing as the cosine of alpha, which we already have the value for. That's 1/4. Alright, I got one more like this, then we're going to do a few trig identities, some very basic trig identities. Alright, you have an angle beta. So this time they give you that the tangent of angle beta equals 5. I'm not the best at drawing Greek symbols or letters, but they give you that the tangent of beta equals 5. In fact, why don't we draw our right triangle with that angle beta? So here's your angle beta right there. The tangent is opposite over adjacent, so that would be 5 over 1. That would mean your hypotenuse is the square root of 26. Okay, so that's going to help you. If you use Pythagorean theorem, you'll come up with your hypotenuse being the square root of 26. Now, what are they asking us for? Easy enough one. They're asking us for the cotangent of beta. Well, the cotangent is just 1 over tangent, so 1 over 5 is, well, just that. You end up getting that the cotangent of beta is 1/5. How about the cosine of beta? The cosine of beta, that's adjacent over hypotenuse, so that'd be 1 over the square root of 26, which would turn into the square root of 26 over 26. So there's your cosine. Now, what is the tangent of 90 degrees minus beta? So you have tangent of 90 degrees minus beta. That's going to be the exact same thing as the cotangent of beta, which we have an established value for of 1/5. So that one's easy enough, another periodic identity. And then they're going to ask you for the cosecant of beta. Cosecant of beta, that's hypotenuse over opposite, so that would be the square root of 26 over 5. So sometimes if you are only given one identity, or sorry, one value, you need to draw a triangle. If you're given two values, then you probably don't need a triangle for it. So there's how you do those type of problems, especially with the periodic identities. Now, we're going to do a few basic trig identity. We're just going to do, I don't want to say they're full-on proofs, but it is part of what you'll encounter in a pre-calc course, verifying trig identities. So we are going to verify the identity. That's going to be our goal for the last set of problems today. Verify the identity. So, for example, you're given that the tangent of theta times the cotangent of theta equals 1. We have to verify that the tangent of theta times the cotangent of theta equals 1. Well, we could do this really in a couple steps. This isn't going to take hardly any time at all. So what you do to verify an identity, you write out the left side all over again. So that means the tangent of theta, cotangent of theta, now equals what? What's true about the cotangent of theta? Isn't that the same thing as 1 divided by tangent of theta? So that's going to equal the tangent of theta times 1 over the tangent of theta, which would cancel those out, therefore giving you 1. So therefore, what you want to write is a therefore with those three triangles. The tangent of theta, cotangent of theta equals 1. We did that in about 2 steps, so that was actually pretty simple. You could have broke down tangent and cotangent into the ratio of sine and cosines, but that was pretty unnecessary. Alright, so we have the cosecant of theta times the tangent of theta equals the secant of theta. So we have to verify that the cosecant of theta times the tangent of theta equals the secant of theta. Well, let's start out again. Let's write out our left-hand side. So the cosecant of theta times the tangent of theta. Now let's break these down. What is the cosecant of theta? Isn't that the same thing as 1 over sine of theta? So that'd be 1 over the sine of theta times, what's your tangent of theta? Well, that's going to end up being the sine of theta over the cosine of theta. Then, of course, you notice your sines cancel out. You're left with 1 divided by the cosine of theta, which 1 over the cosine is the secant. So we've reached what we seek to verify, so we can say that therefore the cosecant of theta tangent of theta equals the secant of theta. So we have just proven that. Let's see here. So next we want to verify that the tangent of theta cosine of theta equals the sine of theta. So the tangent of theta cosine of theta equals the sine of theta. So we're seeking to prove that. So let's write out the left-hand side again real quick. So the tangent of theta cosine of theta equals what? Now, what's tangent? That's the same thing as sine of theta over the cosine of theta. That would be just times the cosine of theta. Well, your cosines cancel out. You're literally just left with the sine of theta. We did that in about 2 steps. So now that you've reached the end of what you were trying to prove, you can say, therefore, the tangent of theta cosine of theta equals the sine of theta. All right, let's see. Cotangent of theta sine of theta equals cosine of theta. So we want to prove that the cotangent of theta sine of theta equals the cosine of theta. Well, let's write out the left-hand side again. So that's going to give you the cotangent of theta sine of theta is equal to, okay, so what's the cotangent? That's always the cosine over the sine, right? So that equals the cosine of the theta divided by the sine of the theta, all that times your sine of theta. Well, your sines cancel out. You're literally just left with the cosine of theta. We were able to do that in about 2 steps. So you can say, therefore, the cotangent of theta sine of theta equals the cosine of theta. Now we're going to spice it up just a little bit here. So you have, let's see, 1 plus the cosine of theta times 1 minus the cosine of theta equals the sine squared of theta. All right. Now, as you get better at these, understanding these identities, you would be able to look at this by inspection and say, that's true, what's there to prove? But for now, we are going to prove it. So let's see, let's do the foiling here. Well, first let's write out the left-hand side. So 1 plus cosine of theta times 1 minus cosine of theta is equal to 1 minus the cosine squared of theta. In fact, I'm going to just write the rest of this in black because I'm starting to run out of ink. So you're now down to 1 minus the cosine squared of theta. Well, what is 1? So isn't 1 the same thing as the cosine squared of theta plus the sine squared of theta? You would have all that minus the cosine squared of theta, which, when you do the like terms, you're literally just left with the sine squared of theta. So therefore, 1 plus the cosine of theta, the quantity of that, times the quantity of 1 minus the cosine of theta equals the sine squared of theta. I think I need a bunch of new color markers. I need a whole bunch of new color markers, and I need them now. Dang it. So, let me get some color markers here. I don't use those as often, but that's about to change. So, here's a good color. All right. So let's see, we are given that the cosecant of theta plus the cotangent of theta, dang it, I wanted to do this in black to start with. Okay, come on. The cosecant of theta plus the cotangent of theta times the quantity of the cosecant of theta minus the cotangent of theta equals 1. We want to prove that. So let's write out that left-hand side again to verify. So this would be the cosecant of theta plus the cotangent of theta times the cosecant of theta minus the cotangent of theta. Now, we can FOIL this out. You'll simply end up getting the cosecant squared of theta minus the cotangent squared of theta. All right, so what is the cosecant squared of theta? Isn't that the same as 1 plus cotangent squared of theta? So we can substitute that in and say 1 plus cotangent squared of theta minus that cotangent squared of theta. Well, what do you know? You're just left with 1. So therefore, we can say that the quantity of the cosecant of theta plus the cotangent of theta times the cosecant of theta minus the cotangent of theta equals 1. We have just proven that. Got a few more proofs, then we're just going to evaluate some angles on the calculator. It won't be too bad, not at all. So, what's the next one? I have two more proofs actually. So we're given that the sine of theta all over the cosine of theta plus the cosine of theta all over the sine of theta is equal to the cosecant of theta times the secant of theta. We have to prove this. So let's go ahead, start out by writing out our left-hand side. So this is going to end up being, of course, write out the original sine of theta over the cosine of theta plus the cosine of theta all over the sine of theta, well, our goal should definitely be to get the same denominator, right? This common denominator would obviously be sine of theta, cosine of theta. So what you should end up getting is the sine squared of theta plus the cosine squared of theta all over the sine of theta, cosine squared of theta. Now you have the same denominator. Well, what is sine squared plus cosine squared? That's just 1, right? So this would turn into 1 over the sine of theta times the cosine of theta, which, if you really want to, you can write this as the quantity of 1 over the sine of theta times the quantity of 1 over the cosine of theta. You can do that. Now, what is 1 over sine? That's the cosecant, right? That is the cosecant of theta, and then 1 over cosine of theta, that's the secant of theta. So we've just proven that. We can now say, therefore, the sine of theta over the cosine of theta plus the cosine of theta over the sine of theta is equal to the cosecant of theta secant of theta. So we just proved that. And I got one more identity we're going to prove. Good one. So we have the tangent of theta plus the cotangent of theta all over the tangent of theta equals the cosecant squared of theta. All right. Well, here's the thing now. We have here, well, first let's write this out. We want to prove that the tangent of theta plus the cotangent of theta all over the tangent of theta equals the cosecant squared of theta. So let's write out the left-hand side again. The tangent of theta plus the cotangent of theta all over the tangent of theta. Well, you have the same denominator for both terms. So in theory, you could split these up into two separate terms. That would equal the tangent of theta all over the tangent of theta plus the cotangent of theta all over the tangent of theta. So what's tangent of theta divided by tangent of theta? That's just 1, right? Plus, okay, we have a cotangent of theta, so you have the cotangent of theta in the numerator, but what about the denominator? Isn't tangent the exact same thing as 1 over cotangent? So this would end up becoming 1 plus cotangent of theta all over 1 over cotangent of theta, which would be 1 plus the cotangent of theta all over 1 times the cotangent of theta all over 1, which equals 1 plus the cotangent squared of theta, which, what's 1 plus cotangent squared? It's cosecant squared. So we actually just proved that. So we can now say, therefore, the tangent of theta plus the cotangent of theta all over the tangent of theta equals the cosecant squared of theta. So there's your proof. All right, now I would like to evaluate a few angles. So this should be fairly easy. Let's say you're given the sine of 41 degrees. So that's easy. You can put that into your calculator. Now, a caveat though, make sure your calculator is in the appropriate mode. If you're dealing with degrees, make sure it's in degree mode, because if it's in radian mode, you're going to get a completely wrong answer. So let's go ahead and do that here. So the sine of 41 degrees, all right, there we go. I just put it into degree mode. So the sine of 41 degrees, which we're going to round to 3 decimal places, would give you about 0.656. So that was easy enough. And you're probably wondering, okay, what the heck is this for? So likewise, we can do the cosine of 87 degrees. The cosine of 87, again, make sure it's in degree mode since you have the degree symbol. So the cosine of 87 degrees gives you about 0.052. Yeah, so the cosine of 87 is approximately 0.052. I should say 87 degrees, not 87 radians. There's a big difference. All right, let's do the tangent of 18 degrees. So you notice on your calculator, most calculators are only set up for sine, cosine, and tangent. We'll get to the cofunctions in a second. But tangent of 18 degrees should be pretty straightforward. You should get about 0.325. So the tangent of 18 degrees is approximately 0.325. That was easy. Now, let's get into something different here. Let's say they want you to find the cotangent of 71 degrees. All right, well, here's the thing. If you have a calculator that has the other trig functions, you're lucky, because most don't. What's true about the cotangent? It would be the same thing as 1 divided by the tangent of 71 degrees. So what you would have to do is take 1 and divide it by that answer. And then you can get an approximate value. So that's usually how you have to calculate these in your calculator. So let's go ahead and do that real quick. So the tangent of 71, now let's take 1 and divide it by that answer. You get about 0.344. So the cotangent of 71 degrees is about 0.344. Let's see, they want you to do the secant of 42 degrees. Again, most calculators don't have a secant function. So what you're going to have to do is use the fact that the secant's the reciprocal of the cosine. That'd be the same as 1 divided by the cosine of 42 degrees. And then now you have it in a form that your calculator will work with. So let's do this here. So the cosine of 42, take 1 and divide it by that, you get about 1.346 for your answer. So the secant of 42 is about 1.346. All right. Yeah, you knew we even had to do a cosecant example. So they want you to find the cosecant of 48 degrees. The cosecant of 48, again, your calculator largely is not going to have a cosecant button, but we know it's the reciprocal of the sine function. So this would be the same as 1 divided by the sine of 48 degrees. See, this is why knowing your basic trig identities is very important, knowing these reciprocal identities. Now you can get an approximate value. So let's find the sine of 48. Now just take 1 and divide it by that answer. You get about 1.346. So the cosecant of 48 degrees is approximately 1.346. So those are all the degree modes. What about in radians? Okay. So let's say you're asked to find the cotangent of pi over 16. That's definitely not one of our special angles, right? So we're going to round this to 3 decimal places. If you don't see a degree symbol at all, if it does not show a degree symbol, it's in radians. So this is where you want to switch your calculator mode to radians. If you keep it in degrees, you'll get a completely wrong answer. It'll make a huge difference. Now, also keep in mind that, again, your calculator more than likely does not have a cotangent button. But we know the cotangent's the reciprocal of the tangent, so this would be the same as 1 divided by the tangent of pi over 16, which now we can get a decimal to approximately 3 decimal places. So this time, since you do not see a degree symbol, make sure it's in radians. So switching to radians, let's take pi divided by 16. Now let me take the tangent of that, and then let me take 1 divided by that answer. You get about, wow, 5.027. So that gives me that the cotangent of pi over 16 is approximately 5.027. Alright, tangent of pi over 8. So we're going to take the tangent of pi over 8. Well, that one's not so bad. We do have a tangent function on our calculator. We can just go straight for it. That won't be so bad at all. Nice to get a break when you can. And again, on the unit circle, or when working with trig a lot, radians are more often than not, they have some form of pi. It's some multiple of pi, but not always. We'll get into that in a minute here. But let's find pi divided by 8. Okay, now let's take the tangent of that answer. You get about 0.414. So the tangent of pi over 8 is approximately equal to 0.414, making sure your calculator's in radians. Now, this is where it can get tricky. They just want you to find the secant of 1.54. You only see a 1.54. Again, if you do not see a degree symbol, nowhere in this do you see a degree symbol. That means it's in radians. This is actually in radians. So make sure it's in radian mode. So your calculator does not have a secant button, but it has a cosine button. We know this is the reciprocal of the cosine function. So you could take 1 over the cosine of 1.54 radians, and then you can get a decimal approximation. So sometimes your radians don't have the pi symbol, but how you know if it's radians or not is if it's degrees, it'll literally have a degree symbol. If it doesn't have that symbol, then it's radians. That's how you'll know. Okay, so the cosine of 1.54 Now let's take 1 and divide it by that answer. You get about 32.477. So the secant of 1.54 is about 32.477. I got one more, then we're done with the lesson. This one's not so bad. We just have a straight up cosine of 1.25. Well, your calculator should definitely have a button here for cosine. If it doesn't, you need to question if you even have a calculator. So, the cosine of 1.25, that's in radians, is approximately 0.315. So this is basic calculation with trig functions. So that's it for this lesson. Next lesson, we're going to teach you how to find trig functions for any angle. This will be where the radius may not necessarily be 1. It'll, more often than not in the next lesson, actually be something other than 1. So I hope everyone has a great day. Take care.